did our pumpkin example where we were picking a sample of size 2. We found every possible mean, and we found that the mean of all of those was the same as the original mean for those pumpkins. So now we're going to repeat this with a group of 5 pumpkins and see if we just got lucky or if there's something to that. So if I pick 5 pumpkins, basically we're leaving 1 pumpkin out. So you could leave out F, you could leave out E, D, C. So then we need the option where we don't include pumpkin B. And then the pumpkin, or the option where we don't include pumpkin A. Okay, so to do this, we add up our weights. So the weight of A was 19, C is 15, D was 9, E was 10, F is 17. So to get our mean, add those up. And divide by 5, since it's 5 pumpkins. And we get 14. And if we leave off pumpkin A, okay, so if we look at this, how many different samples did we create? 6 different samples. So the probability of each of these samples would be 1/6. So same probability for all of them because we're looking at the sample probability. All right. So if we look at this, what is the mean? So how do I find the mean of these means? Is that confusing? Yep, add them up, divide by 6. I did ask my questions out of order. If I do that, we get 84 divided by 6, which is 14. Have we seen that number before? Yeah, that was the average we got when we had a sample of 2 pumpkins. That was also the average weight for the original 6 pumpkins. So I think there's something to this. Let's talk about the error in those. So if I just made a basic graph here. Let's I'm going to plot all the different means we got. So first I'm going to do it with when we had a sample of 2. So looking back in our notes, when we had a sample of 2, all the different means we had 16.5, 17, I'm just putting a dot for each of those. 14. Do you guys all know where I'm getting these numbers? So that was just all the means from that table we completed yesterday. Now, if we look at when we had a sample of size 5, let's plot those. My means were 13.4, 13.8, 15, 13.8, 13, and 14. What do you notice about the two groups? It got smaller, so the error decreased. So there was less spread when n equals 5. So that means smaller error. And if we think about that, that seems reasonable because the probability that we got the true mean this time was the probability that I got a 14, and the probability of that was 1/6, right? But the first time I did it, the probability that I got the actual mean was 1 in 15. So as my sample became larger, it was more likely that my sample mean matched the real mean, and there was less error in my data, which should seem reasonable. The more pumpkins we're including, the less chance of error there will be. So, the question here, what role does n, the sample size, play in the standard deviation? So, how does my n impact my standard deviation, which we know is a measure of the error? When n gets larger, what happens to our error? It gets smaller. So, the larger the n, the smaller the standard deviation, which should seem reasonable. The more people you include in your sample, the more accurate your sample will be. All right, so we just looked at 2 examples of a distribution of sample means. Basically, every possible sample, finding the mean of each. Now we need some characteristics of this. So we know, if you look at your lovely formula sheet. So we just got done talking about the normal distribution, and we did all that. So we are in chapter 8. First thing that we have is the mean and standard deviation for the sampling distribution of the sample means. I'm going to do this. So for the mean, and we put x bar for the sample means, so this means the mean of the sample means is the same as the mean of the original population, which we saw with our pumpkins. Every sample had the same mean. The standard deviation of the sample means is the sample standard deviation divided by n, and that's why it will get smaller as n gets bigger. And then if x is normally distributed, so is x bar. So if the original data is normal, then the sample means will be normal as well. And why is normal good? How can we find probabilities? From the normal table. Okay, so if it's normal data, we can look up our probabilities on that table. So we have to convert it to a z first. So our z will use the mean and standard deviation for x bar, if we're talking about our sample means. And then it's the same thing that we were doing before. So let's look at an example. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 and a standard deviation of 0.02. Okay, this is for all the pennies. So it's saying like the mean of all of my data is 2.46. The standard deviation of all my data is 0.02 of all pennies. So find the mean and standard deviation of the sampling distribution of 200 simple random samples. So if I had 200 samples of pennies, what would my mean and standard deviation be? So the mean of my sample means would be 2.46. Standard deviation of the sample means would be I wrote something down wrong. This should be the square root of n. Sorry about that. So 0.02 divided by the square root of 200. Okay, so that gives me 0.0014. So if I ask for the mean and standard deviation of a sampling distribution of 100 simple random samples, what's the mean going to be? And my standard deviation? And notice this one had a bigger standard deviation because my sample was smaller. Okay, let's try an example involving this. So still dealing with these pennies. So normally distributed mean standard deviation, same as on the last slide. So the question is, what is the probability that in a simple random sample of 10 pennies minted after 1982, we get a sample mean of at least 2.465 grams? So we're finding the probability that the sample mean is at least, so greater than or equal to, 2.465. Okay, first thing to check, I did tell you it was normally distributed, so that means we can use our normal table. But what am I going to have to do to this first? To get my z, I need the mean and standard deviation that match my variable. My variable is x bar, so I need the mean and standard deviation for x bar. The mean for x bar is the same as the population mean, so that's 2.46. The standard deviation would be my 0.02 divided by what? So now to get our z, it's our value minus the mean divided by the standard deviation. Don't round your standard deviation too much, because since we're dividing by it, the more you round, the further off your z is going to be. So please keep at least 4 decimal places. Also, show me what you're using so I know if you have a slightly different answer. I know if it's due to rounding error or what. So I get a z of 0.79. So we need to find probably that z is greater than 0.79. How do we do greater than from our table? And then we look up 0.79, and that is 0.2148. Is that okay? So let's try another. The engines made by Ford for speedboats had an average power of 220 horsepower and standard deviation of 15 horsepower. A potential buyer intends to take a sample of 4 engines and will not place an order if the sample mean is less than 215 horsepower. What's the probability they will not place the order? So if they don't place it, that means the mean, because I'm talking about sample mean, so that tells me X bar. If he doesn't place it, that means the mean was what? Alright. What is the, since I'm talking about X bar, to get my Z, I need the mean for X bar and standard deviation for X bar. What is the mean for X bar? 220, same as the population. The standard deviation would be what? Divide by the square root of 4. So we get 7.5. So we now get our Z. So our value, 215, minus the mean, 220. Divide by the standard deviation, 7.5. And we get a Z as negative 0.67. So we need probability Z is less than negative 0.67. And less than is what our table gives us, so we just read the number from our table and we get I want you guys to try the next one. So we want the probability, the sample mean is greater than 110. So the mean of the sample means is the same as the original mean, 100. Standard deviation of the sample means is the original standard deviation divided by the square root of n. So it doesn't come out to be pretty. Keep at least 4 decimal places. So 4.7434. So our Z is our value minus the mean divided by standard deviation. So we get 2.11 if you round accordingly. So we're finding the probability that Z is greater than 2.11. Greater than means 1 minus, so probability on the table, 2.11 is 0.9826, and we get 0.017. Alright, is this going okay? Alright, good. Moving on then. If I asked you about rolling die, okay, that's an example we've used a lot. If I take that probability distribution, would that be a normal distribution? What's the probability, if you think about our outcomes, what's the probability of getting a 1? What's the probability of a 2? Probability of a 3? What kind of distribution has everything with the same probability? Uniform. This is uniform. Because everything has the same probability. But then I want to show you something on the next one. If I take a graph, so this is a sampling distribution of the sample means when I had 200 samples of size 4. So I had Basically, I rolled my die 4 times, got the average, and I did that 200 times. Okay, and then this is when I had 10 in my sample and 30 in my sample. What do you notice about these? They're kind of normal. What's happening as my N gets bigger? It's getting more and more bell-shaped. So if my N is big enough, would this be a normal distribution? Okay. So it actually turns out that the shape becomes normal as the sample size increases, regardless of the original data. So even if the original data isn't normal, if our N gets big enough, the sampling distribution and sample means will become normal. In general, if N is greater than 30, we can assume it's normal. If N is less than 30, the original data must be normal. So no matter what, the mean is equal to the mean of the original population. Standard deviation is sigma divided by square root of n. That doesn't change. But to decide if we can treat it like a normal distribution, either the original data had to be normal or our sample size has to be more than 30. So, let's skip that because that's what I've already talked about. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes and standard deviation is 3.2 minutes. If a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. When I ask you to describe it, I'm asking for 3 things. Did I tell you that the original data was normal? No. Can I assume it's normal? Yes. So we need to make note of that. If you don't jot anything down, I'm going to assume you didn't even think about it. So I'm just going to say n is greater than 30, so that means it is normal. Okay, when I say describe, the other 2 things I want are the mean and the standard deviation. So the mean for my sample means would be, and my standard deviation would be 3.2 divided by the square root of 35. So that gives us 0.5409. Okay. So then part B, if a sample of 35 is selected, what's the probability that the mean oil change time, so the mean x bar, is less than 11? So we need to get our z, so r value minus the mean that we found in part A divided by the standard deviation. We get a negative 0.74. Probability z is less than negative 0.74. And that is 0.2296. So is this good advertising on their part? I mean, it sounds good if you can get your oil changed in 10 minutes, but it's actually less than a 4th chance that it takes under 11 minutes. So they're really not under 10 minutes. All right, last one. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. If we have a sample of 35 and determine the mean weight was 36.2, does this result suggest anything unusual? So, did I tell you it was normal? No. So if I don't tell you it's normal, you need to make note. N is bigger than 30, so that means it is close enough to normal. We can use it. So what is our standard deviation of x bar? And I said standard deviation, I meant mean. I wrote mean instead. Standard deviation would be? So we get a standard deviation of 2.805. So if I'm trying to decide if it's unusual that they gained 36 pounds, can we do the probability that something equals 36.2? I can take care of that one. Can we do equal to from our normal table? No, we either have to do less than or greater than. Okay, so if you think about it, if the mean is 30, if I find the probability that I'm less than this, is that telling me anything? No, because I would expect it to be less than. So if I really want to figure out if this is unusual, let's find the probability that we are bigger than that. So we have to get our z. So r value minus the mean divided by standard deviation. So we'll find probability z is greater than 2.84. So greater than, we have to do 1 minus. That is 0.9977. You get 0.0023. So, is this unusual? Yes. So what that means is either we had a bad sample for one reason or another, or the mean has changed and it's no longer 30 pounds. So we don't necessarily know why it's unusual just from this, we just know that something is going on here because we really shouldn't see this happening. All right, any questions for me? All right, so you guys have, no, you don't have the chapter 18, but let me give you the homework.